Hello, everyone. Welcome to session P14 of the main track. The topic is testing, and we have a variety of papers ranging from very traditional topic, testing file system implementation, up to testing robustness of deep neural networks. So it will be an interesting session for everyone. So we will start by the first talk, which will be given by Dehai, and then the paper title is See Normally Vision-based linting of GUI animation effects against design don't guidelines. The attendees in the room, please post your questions in the Slido window on the left side of the Clouder, and then we will have the QA session after the presentation. Okay, Dehai, please start your screen sharing.
Okay. So, okay. Hello, everyone. I'm Dehai, and I'm from the Australian National University. This is my presentation today. See, normally, vision-based linting of GUI animation effects against the design don't guidelines. Mobile platforms provide GUI design guidelines, such as Google Material Design for developers. Here are examples from Google Material Design. It says expand the card to reveal information, but don't flip over to reveal information. Another example is about a bottom sheet. It says use a visible screen with model bottom sheet to inform users cannot interact with the rest of the screen, but don't use an invisible screen for model bottom sheets. The guidelines makes GUI more appealing and more usable for users, but the guideline documentation has so many rules, which makes it impossible for developers to remember all of them. So in this work, we try to design a tool to automatically validate the GUI animation against the design don't guidelines. So here are more examples, and if we just extract feature using a CNN that is pre-trained on ImageNet, we can see the examples are distributed randomly in this feature space because CNN only focuses on the pixel level features. But in this work, we have to consider the animation, foreground, background, and the combination of them. So previous work used computer vision-based method to detect the violation of the implemented GUI against the GUI design. However, their technique only focuses on static GUIs, and they assume that the two GUIs are largely similar but have minor difference. But for guidelines, do and don't are not necessarily similar. We also try to make it as a multi-class section classification problem, but we found it doesn't work in our task. Firstly, if we are new category, we have to update our network. And it is pretty hard to collect enough data to train our neural network, especially for the don't examples. So in this work, we propose an unsupervised deep learning method to solve the GUI linting problem. We firstly use the unlabeled GUI animation to train the vision-based GUI animation feature extractor to extract the spatial temporal feature from the GUI animations. After training, we use the trained feature extractor to map a few typical GUI animations to a dense vector space. When input a linted GUI animation, it is also mapped in this feature space. And finally use KN search the most similar violating GUI animation. This is the architecture of our network, which is based on variational autoencoder and generative adversarial network. The VAE learns to reconstruct the GUI animations, and GAN enhances capability of reconstruction. We also use an additional feature encoder to learn more abstract features from the reconstructed GUI. After training, we use the encoder and the additional feature encoder to extract features from GUI animations. So by using our method, we can see the random distributed examples are clustered. And we can see the same animation are located at the same position. But note that the GUIs with same animation but different vision effects are located at different position. For example, this is the same animation that is pop-up window, but for the number one, it has black background and a shadow, and which means the pop-up window can be distinguished clearly from the background. So it's taken as the normal example. But for number two, it doesn't have a shadow, so it's taken as violating example. And another example is the bottom sheet. Number three, it has black backgrounds, but number four, it doesn't have black background. So number four is taken as violating example. In this work, we consider non-don't categories, and it involves various kinds of animations and components like a banner, pop-up window, snack bar, and so forth. We prepare two data sets for evaluating our work. That is real-world data set and a synthetic data set. The real-world data set is from the website, such as Goguryeo data set and online blogs. And we finally collect over 90,000 examples for evaluating the model. And the synthetic data is generated manually to expand the data set for evaluation. We firstly collect the components like pop-up window, banners, and here are background, that is a screenshot.
听不到声音啊，你那个 room 也听不到声音是吧？
So, can I go on?
Please continue.
Okay. We just select the materials randomly and just paste the component on the background. So we just generate the synthetic data like this. As the materials are selected randomly, here are some unreasonable data. For example, you cannot paste a pop-up window upon another pop-up window. So we just manually remove the unreasonable data to make the synthetic data looks like the real world data. In this work, we consider the 4 research questions. And because due to the time constraint, I only show the effectiveness result on real world GUI animations. This is the result of accuracy and F1 score. And T is the number of typical GUI animation examples of design don't guideline in the search service. And the K is the number of nearest neighbors that would for the design don't guideline violated by the limited GUI animation.
1 minute.
You can see increase. Okay, increasing T can increase continuously improve the performance, which means more examples in the search space, the more comprehensive the search space becomes. However, there are some failure examples. This is snack bar blocks bottom bar. We can see both of them are black in color, dark in color, and mixed together, which means it's very hard to recognize. And our model failed to give it a right category. So it's taken as normal GUI animation, but it's actually the snack bar blocks bottom bar. Another example is pop-up window. We can see this one has shadow, but this one doesn't have shadow. So actually this one is normal, but this one is the violating one, but it looks very similar. Okay, that is it in my presentation. Thanks for your time, and I'm happy to answer your question here.
Okay, thank you, Dihai, for sticking precisely to the time. Do we have any questions for the speaker? Okay, here's one from the Slido window. The question is, can you comment on the total amount of time you spent for manual preparation and analysis of the data? I think the question refers to the manual filtering that you did.
Wait, sorry, could you please repeat it?
Okay. Can you comment on the total amount of time you spent for manual preparation and analysis of the data?
So the total time?
Total time that went into manual preparation of the data. For example, you had to discard any unrealistic animations manually. So how much time did it take?
Ah, okay. It takes like maybe 2 weeks. Actually, I can't remember it clearly, but actually it's actually a large manual work. So maybe it takes a long time, but I can't remember it clearly. Maybe 1 week or 2 weeks.
Okay, I'll just ask one more very quick one. How did you label do's and don't examples for the training?
Actually, our neural network, it's actually a surprise method. So we don't need to label it. We just train a network to map the examples to the feature space, and it's actually not a classification, not a supervised learning classification problem. We just choose some don't examples and put it in the feature space. And when you input a linted GUI, we just search the most similar one from the search space and identify it as the most similar one, the most similar category. So actually, it's an unsupervised learning. So we don't need to label it.
Okay, thank you very much. Just remember that there will be rooms dedicated for each paper, and then you can continue any question or discussion over there. Thank you, Dehai. So we'll now move on to the second question, which will be given by, thank you, which will be given by Xiang Gao. The paper title is Fast Testing-Based Data Augmentation to Improve Robustness of Deep Neural Networks. I think this is a topic that's of interest to many people, and Xiang started the screen share, so I'm going to give it to you.
So thanks for the introduction. Can you see my screen?
Yes.
Okay, great. Hello, everyone. Thanks for your attending. I'm Xiang Gao from National University of Singapore. In this talk, I will present fast testing-based data augmentation to improve robustness of deep neural network. This work was mainly done when I was an intern at Fujitsu Lab of America. This is their joint work with Ripon Saha, Mukul Prasad, and Abhikri Chaudhary. In recent years, neural networks are widely applied in many applications like autonomous driving, medical diagnosis, malware detection, and so on. By training a model on the training dataset, AI model could achieve good accuracy on the testing set. However, good accuracy does not mean good robustness. That is, if we slightly perturb the testing set, the model will misclassify them. For instance, the model could correctly classify an image. However, after rotating the image a little bit, the model will misclassify it. So in this project, we targeted to improve the robustness of AI model from the perspective of software engineering. Data augmentation is an approach to improve performance of AI models. Similarly, it can also be used to improve model robustness. In a widely used setting, people first find some representative perturbation of the training dataset in each epoch, and then train the model using those perturbations. However, generating representative perturbation is not easy, especially when the space of perturbation is huge. So our first challenge lies in how to identify representative perturbation from huge space. Existing approach randomly generate perturbations. As shown in our evaluation, those approaches are not effective enough. Our second challenge is that data augmentation must be efficient enough to save the valuable training time. Before going into the technical detail, let me first give some background of fuzzing. Gray box fuzzing is a widely used text case generation technique. Typically, given some seed input, you mutate the seed input and generate a set of mutations, and then you will test your program on the mutations and retain the interesting ones that can improve coverage. Based on that, you will put the interesting test as new seed, and this process continue with the goal of achieving higher code coverage. Our insight here is that the interactive nature of fuzzing get overlaid on the multi-epoch training of DNN. To improve robustness of AI model, we investigate a new data augmentation based on fuzzing-based approach. Here is the overall structure of our fuzzing-based data augmentation. Basically, for each data point in each epoch, we train the model using its representative perturbation. The representative perturbation is also used as the seed image of the next epoch. This process is just similar to the fuzzing loop. Our data augmentation is composed of two main components. The first component generates representative perturbations by first generating a population of perturbations and selecting the most interesting ones among them. The second component is selective augmentation. In order to improve the efficiency of data augmentation, our insight here is that not all data points in the training dataset are difficult to learn. We may selectively augment parts of the example that may confuse the model. Now let me give more details of those two components. In the normal training formulation, the training goal is to minimize the loss over the training dataset. To generate a robust model, instead of minimize the loss over the original training set, the new formulation assumes that we first perturb the training set and minimize the loss over the worst perturbations of the training set. So in our evaluation, in our approach, we are using fuzzing-based technique to generate the worst perturbations. Here is an example with two transformations, rotation and translation. In the first epoch, we train a model using the original image. From the second epoch, we first generate a set of perturbations and select the worst one with highest loss. The selected perturbation will be used to train a model in the second epoch, and also it will be used as the seed image in the third epoch. This process continues until we can train a robust model. As I just mentioned, conventional method augment each data point, which is inefficient. We save significant amount of training time by skipping some data points, which is presented using red cells in the figure. Our main idea is that we can skip to augment some data point that is already point-wise robust. We define the point-wise robustness based on loss. For a given data point X, we first generate its perturbations and then generate the corresponding loss. If the maximized loss is less than a threshold, we regard X as a point-wise robust point, which will be skipped in the selective augmentation. We implement our idea in a tool called Sensei and evaluate on 5 widely used data sets and 15 existing models. We evaluate the robustness using robust accuracy. Basically, a data point is regarded to be robust if all its realistic variations are correctly classified. Under this setting, the robust accuracy measures the percentage of robust data points. We define the space of realistic variation using 6 transformation operators, which include 3 spatial transformation and 3 non-spatial transformations. We choose the transformation parameter according to existing paper. The transformation parameter makes sure the variation are still valid image. For instance, we restrict the rotation range from minus 30 degree to 30 degree to make sure the rotated image are still valid. To evaluate the effectiveness of Sensei, we compare it with several baselines. Original model does not perform any data augmentation. Random approach randomly augmented the data set. And the worst of time is the state-of-the-art approach. we compare the robust accuracy of those approaches. Our evaluation showed that Sensei can improve the robust accuracy on all 15 models by up to 12%. Further, we evaluate the effectiveness of selective augmentation by measuring the training time. Our evaluation results show that selective augmentation can reduce the average training time by 25%, while does not lose too much robust accuracy. On conclusion, we propose a fuzzing-based data augmentation to improve the robustness of AI models, and we implement our idea in a tool called Sensei, which is open source available on GitHub. Compared with the state-of-the-art approach, we show that the Sensei improves robust accuracy by up to 12% and 5.5% on average, and reduce the training time by 25%. This also led to the end of my presentation. I'm glad to take if you have any questions.
Okay, thank you for keeping to the time. We have a couple of questions in the Slido window. The first one asked by Saikat at UIUC. The question is it assumed that your perturbations do not change the label of the data point / image? Yes,
exactly. But because as I just mentioned, we have some transformation operator and some parameters to limit the transformed image are still valid, and to limit the variation is still similar to the original image, so that we can preserve the existing label.
Okay, thank you. I'll move on to the next one. Jeremy asks, your approach focuses on first testing based augmentation of image dataset. Could your approach be extended to work with video data or natural language data, so in general data in other domains?
Conceptually, I think we can, because our approach just work on the data augmentation, and we didn't change the model itself. So to extend our approach to other domain, we may need to define different transformation operators. For image, we define the transformation operators as rotation, translation. For the other domain, we may need to define different transformation operators. Our evaluation, we just work on the image dataset, but conceptually, I think we can also work on the other domain.
Okay, so I'll try to add one more because I think we have just the time. To drop training images, I think you need to check robustness of image neighborhood, which will take some time. Was this time counted for RQ2?
Yes, exactly. We need to generate the worst perturbations from a population of perturbation. It takes time. We already counted the time when we measure the training time. Okay, thank you, Xiang, for a very interesting talk. We're not hearing that applause effect today, but I'm sure everyone is feeling the same. Okay, thank you. So we'll move on to the next presentation, which will be given by Emily Kovalchuk from Apple. The paper title is Modeling and Ranking Flaky Tests at Apple. So Emily, can you start your screen share, please?
Yes. Easy. Okay, great, thanks. So I'm going to share some work our group's been doing to reduce test flakiness in service testing, where all tests can be flaky. But first, just a quick definition of what we mean by test flakiness. So this is the most basic example. We have one test, we run it once, and it passes. We don't change anything in the test. We don't change anything in the code we're testing. We run it again, and we get a fail. This variation in the results without changing anything in our test or in the code we're testing is what we call flakiness. And it can happen for a number of different reasons. It's normally some sort of non-determinism in the code or the test. And it could be something like a number generator or some order dependency, network issues, or database availability issues. The problem with this is that it's very hard to interpret the results It's probably going to require some manual work. It's going to prevent us from automating things. It's hard to reproduce, which might actually make it hard to fix. And if this happens to too many of our tests, we're going to start to lose confidence in what our results mean, might start letting faults through as we ignore the results. Our specific work addresses a specific situation in service testing, and it looks something like this. So we have these test cases. These are basically like service request templates, and we populate them with data. So an example would be like a search service request that's populated with a query string. And we send those over in large suites, about tens of thousands of tests. And they hit this very complex distributed service. It has a lot of different dependencies, a lot of varying levels of control here. Some would be within our direct org, some might be outside our org within the company or a third-party provider. Might have ML components that act non-deterministically. And it might actually take various paths through the service depending on the run to do different failure handling techniques. So if we have availability issues or network issues, it might actually take a different route. This is important in this situation because in this context, all of our tests actually have this flaky dependency and can therefore be flaky. So any of these nodes or databases could have an availability issue in a run. We might have network issues, et cetera. And when we have this many tests, we can't expect each flaky test. So we need a way to prioritize where to look. So this was our approach, what we did. We developed a model that allowed us to quantify how flaky a test is. I'm gonna, just in the interest of time, I'm not gonna go into too much detail about the model, but I invite you to look at the paper where it's formalized. But at a high level, it looks something like this. We have these test results. There's this code version change or a version change. Something significantly changes in the system you're testing. And we look at variation within that version and across versions. So a test that is flaking often within a certain app version or code version, and doing that consistently over different releases is going to be more flaky than something that's not flaking within any versions or is flaking rarely within a single version. So examples here are test 1, we can see is not flaky because it's failing consistently on this last code change, block of runs on a code change. Test 2 is more flaky, test 3 is less flaky, and test 4 is not flaky. We also attach a confidence value, just giving us some indication of how confident we are in that score, mainly based on the amount of data we have. So example here, test 4 might have been a new test. We only have 3 runs, so it has a smaller confidence than the other tests. We've implemented these models and we use them in practice. So here's an example of the API where users can get up-to-date scores, update the scores every hour. And we've been computing over 100 million scores a month for over a year now. Again, in the interest of time, I'm going to skip straight to RQ2, though I encourage you to check out the paper to look at RQ1, where we evaluate the accuracy of the models and ranking. And then I'll be skipping another RQ as well. So definitely check out the paper for more details. But in RQ2, we looked at 2 things. We used the best performing model to look at how does test flakiness impact 2 CI pipelines at Apple, and then how is the flakiness spread across our tests. And so here are the results. We looked at 2 data sets, R1 and R2, and we first looked at just the percentage of tests that flaked within each data set. So they're both a couple months worth of test results. R1 has 1 suite, R2 has 3 suites. And any test that had any variation on what we called that version was going to be a flaky test, and it only had to do it once. What we can see is that R1 both had pretty high numbers. So 59% of its tests were flaking, in R2, 36%. And since we're talking about thousands of tests, this is pretty much the motivation for needing a model like this. That's more than we can inspect. We can dive deeper into the actual distribution of the scores and start to understand how flakiness is actually impacting them a bit differently. So in R1, we can see the scores are actually very low. Like the mean is basically a flip 1 in every maybe 100 runs or so. There are some outliers with the max being about a 0.3. So that's roughly something like 3 flips in every 10 runs. But R2 is actually much more targeted. So not only is it hitting only a smaller portion of our tests, but it's actually doing it in a repeated way. So these flaky tests are flaking in a very repetitive manner, the mean falling around 0.1, 0.2, and then many outliers, that's something like 3,000 that are actually ranging from 0.4 to 1. In our next RQ, we tried to understand if we could use the scores to actually triage what was causing those flaky tests in R2. So we saw that repetitive behavior. Could we start to understand what was causing it and use the scores for triage? And here we can see we factored out various components to do this. So that data set had multiple environments, a post-merge environment, and then 2 sort of sign-off environments, and then multiple suites which test different subservices. And so here in this plot, we've factored out each environment. We've actually factored out each suite. And we tried to look at how it would actually impact the scores and the ranges, indicating if a certain factor was contributing to the flakiness. We were able to identify 3 causes, each starred. So the first here in yellow was an environment issue. We can see scores are much higher on this post-merge environment, which is actually a bit different than the others. It's using spun up dependencies, not static stable dependencies. It's particularly bad here in this first test suite. That's been confirmed. And then the second one over here was a more suite-specific issue. We can see there's flakiness on this EW and TS1. This was actually unexpected because we shouldn't have enough runs to observe flakiness on this environment. So it suggested something was up. Developers confirmed there was a bug here in the test infrastructure, which has been fixed. And we're now down to about less than 1% observable flakiness on this environment. And then last, we looked at test suite 2. We can kind of see that in this daily environment that's more stable, it's actually still the highest flakiness, as well as in EPM, it's flaking pretty consistently there as well. We targeted that subservice to understand what might be causing it. Does it have a certain component maybe that it's using that's unreliable? And devs have, we've reported this to dev, and they've been able to fix various different test and infra issues. And so we've seen numbers decrease pretty significantly there as well, going from about 10% flaky tests to less than 3. Last, we were able to reduce flakiness by using the scores for triage, but we also wanted to do this in a slightly more automatic way. So we looked at what the trade-offs would be if we started filtering out results per run that were above a certain threshold. These would be particularly flaky tests. We want to see the trade-off in flake reduction versus loss and fault detection. We modeled this by basically the percentage of failures that were in those inconsistent versions would be flake reduction. Loss and fault detection would be the loss of failures in those consistent failings. Able to get some decent results where we can see certain environments did better than others in reducing. All could reduce, but the loss and fault detection was a bit less. And some environments did best in these daily and weekly, where we actually able to remove about 44% of those flaking failures with less than 1% loss and fault detection. A note on that is ideally we want this to be 0, just to clarify. And also we can't say for sure flakes are not faults. However, something like this might actually be useful in certain stages of testing, like CI or sign-off.
I think we want to move on to the question. Yeah, okay, that's summary.
Summary, just to summarize of what's going on, we proposed, formalized, and evaluated the flakiness models. We measured the impact on 2 pipelines where we could actually see the difference of how flakiness was impacting them. And then we demonstrated uses for reducing. So the triage, 3 confirmed issues, able to get our weekly down to less than 1%. And then the filtering where we're able to get a reduction of 44%.
Thank you very much. So I'll go straight into the question, which is from Wing at UIUC. The question goes, when developers get the scores for their test, is this when they make changes to the test suite or to code? Have developers found the score to help debugging?
Yeah, for sure. So we've seen significant improvements by using the scores. It allows us to know which tests might be flying under the radar and then associate them with certain environments, understand that certain environment issues might be happening, We can also do factorization like that across our frames or different tests and group similar tests together to see certain dependencies might be impacting them.
Okay, yeah. You're getting a lot of questions. I'll move on to the second one. Can you reduce the flakiness on environment? Is this a case where the service has to run on different environments rather than the tests?
What's that?
So how can you fix the environments to be less flaky?
Sure. So what ends up happening is actually each environment might be set up slightly different. So like that post-merge environment was actually using some, note again that it's very distributed. So it was actually using spun up environments like Kubernetes sort of thing for certain dependencies, which were less reliable than the static ones in the other environments. They might actually have different like caching, QPS, lots of different things could actually vary between the environments.
Okay, so I'll do one more. This is again from Jeremy Bradbury. Could you comment more broadly about how flaky tests are triaged, addressed, are most related to errors in testing tools or source code environments? So I think the question is about the distribution of the causes.
Yeah, so you mean like where we've seen problems most commonly? That's a slightly difficult question. I would say certainly due to the types of tests we're looking at, there are, the environment is definitely impactful, but we've definitely caught service issues. We've definitely caught test issues with our assertions being too, maybe too specific.
Okay,
yeah.
So I think the questions will be moved to the paper-specific discussion room. So you please ask Emily further questions, and then you can continue the discussion over there. Thank you very much.
Thank you.
So we will move on to the next talk, which will be given by Dongjae Chen. The paper title is Testing File System Implementations on Layered Models. Okay, can we start the presentation, please?
我感觉能说话，但是好像没有。
Sorry, we seem to be having a slight technical problems. We will start the presentation shortly again with sound.
This is Dongjae Chen from Nanjing University. In this talk, we will talk about how model benefits input generation in testing systems and how to build a layered model for complex systems. Software testing, or finding inputs to manifest bugs, is an old problem. It's analogous to finding stars in an extremely huge universe. Generating effective inputs has challenges. The inputs should be syntactically correct. This is the easy part because complex systems may have simple input formats like systems and key value storages. The hard problem is that we should generate inputs that are semantically valid, and these inputs should be diverse. We will talk about them in detail next. We can either randomly sample inputs in the whole space or mutate the existing to generate new inputs. The fuzzing is the most powerful tool for complex systems nowadays, but it may get trapped in a local region easily, because it does the local search and generate inputs may be similar. On the other hand, sampling is able to see the entire space, but since most inputs are semantically invalid even they are syntactically correct, It's easier to sample invalid inputs, like hitting the vacuum in the universe. In this paper, we present a better sampling with models. Models specify which inputs are valid or not. That is, it constructs an input space. There are no invalid inputs. In this way, we can avoid sampling invalid inputs and guide sampling, or even guide fuzzing. For example, a file system model should specify that before opening a file, it must exist in the system. But consider that there are much more other complex system calls and obscure parameters. It's difficult to build such a model. So in practice, building a process model for real systems is intractable because they are too complex and support too many features. We find that the evolution of software may serve as hints to build models for complex systems. Complex systems are just like aircraft carriers. There are many components in it, and these components interact with each other, so the system is too complex to model it directly. But actually, not all aircraft carriers are such complicated. The first aircraft carrier was just converted from a collier by adding daggers and some other simple components. Then it evolves into the concurrent complex one. So if we are modeling the first aircraft carrier, it's much easier. Again, let's move forward. The first aircraft carrier is also developed from other simple shapes, so modeling these shapes also becomes easier. Analogously, complex systems are also developed from original versions by adding various features. So we can model the original systems, but we are testing the complex ones. So how can we bridge the gap? The answer is the evolution. Since we can model the original system, we can build a simple and process model for it first, and use this model to sample inputs. These inputs are valid and diverse, and they target the fundamental functionalities of systems. Then, similar to the evolution, we can refine these inputs to manifest other various features of the system. Since these features are hard to model precisely, the refinement is relaxed as long as it keeps the correctness and diversity that are produced in the simple model. First, we build a simple model, and in this model, sampling semantically correct and diverse inputs. Then we refine these inputs to manifest other system features, but at the same time, we should preserve semantically correct and diverse generated in the first model. And at last, we have a syntax model which refine inputs into syntactically correct ones. We implemented this approach into testing file systems. First, we have a core model which organizes file structures, that is, the fundamental functionality of all file systems. The state can be represented as a structure graph, and we use a stateful model checker to generate diverse inputs. Second, we have a core extension model, which refines these inputs to manifest other file system features like journaling, caching, and still it preserves states in the core model. At last, we have a syntax model. It just refines the inputs into syntactically correct. Let's take an example to see the whole generation. This input crash is F2FS and can be generated by our later model. First, we need a complex file structure. There is a directory with depth 5. In core model, we generate many inputs result in diverse structures, so the core model is able to generate such a structure. And at the same time, we need plenty of I/O operations, which may manifest file system journaling, caching, or other features. The core extension model manifests these features and provide high-level system calls. Finally, the syntax model fills random parameters, and these parameters may trigger other complex file system features. We developed a prototype tool named Dogfood and evaluated it with different checkers to see whether it can benefit these checkers and detect real file system bugs. We choose 6 popular file systems like ext4, betafs, which are provided in the Linux kernel. In the first experiment, we compared Dogfood with Zscaler. Both of them tested in a 12-hour running, and we found that Dogfood was able to find hundreds of crashes much more than Zscaler. We report some of crashes as bugs to the developers, and some of them were fixed quickly. In the second experiment, we compared Dogfood with Ace using a crash consistent checker. Each of them generated 1,000 inputs to the checker, and we can see that Dogfood helped the checker detect much more issues, and it benefits the checker a lot. Finally, let's make a summary. We see that finding inputs to manifest bugs in software testing is an old and difficult problem. And a model may offer surprises sampling such inputs, but in practice, building models for complex systems is intractable, and we found that the evolution of software may serve as hints for building layered models, which can help generate inputs. The experiments show the power of our layered models. Thank you.
However,
Okay, thank you for the presentation. Is there any question for Dongjie? I haven't seen anything on Slido yet, but if you have any, now would be a good time to ask. Or I can start by asking one. So how let's say expensive is it to come up with the layered models? Can we, if you have a complex one, can you systematically break it down into layers, or do you have to write it from the scratch? Hello? Okay, the internet connection seems to be a problem here. So I think we will use the offline channel for text channel for questions for this paper, and then we will move on to the next paper to keep the session in time. So I will introduce the next presentation, which will be given by Shinhao Jin. And then the paper title is a cost-efficient approach to building in continuous integration. Shinhao, can you start your screen share, please?
yes.
Thank you.
Thanks for the introduction. Hello, everyone. Welcome to my presentation. Today, I'm excited to present our work of a novel build selection approach to reduce cost in continuous integration. Continuous integration, or what we call CI, is a popular practice in modern software engineering that encourages developers to build and test their software in frequent intervals. Unfortunately, this is also a high-cost process. CI is expensive because there is a high workload from computation in the system. To solve this problem, our approach targets saving the computation cost produced in continuous integration. First, let me introduce how we can reduce the cost. This is an example CI timeline. When you make a change, CI engine is triggered to test your code. If the process is successful, the build is considered passed, such as build 1. Sometimes there is an error in the code and the build is failed, such as build 2. Then, for example, developers run their builds, sometimes they pass and sometimes they fail. The expense of CI is so high because there is an overload of builds. This is because developers are encouraged to build whenever they make a code change. To reduce the cost, we intend to only select a subset of builds to execute. The value of CI mostly focuses on letting developers find bugs early, and since only failing builds are actionable, we target skipping passing builds to keep the value of CI. This ideal timeline is the perfect situation to save effort. Skip every passing build and execute all failing builds. We depict the skip build with a dashed circle. To reduce the cost by skipping passing builds, first, we want to identify how prevalent are passing builds. We hypothesize that most builds in CI return a passing result. If this is true, they will show an opportunity for strong savings in build effort. So to evaluate this, we did the first empirical study on the Travis torrent dataset of over 300 projects and found that 88% of builds are passing builds. This result supports our hypothesis that skipping passing builds would strongly save build effort in CI. So we also want to keep the value of CI, so we don't want to skip failing builds. We make an observation that there often exists a sequence of builds that have the same build result. In other words, failing builds are likely to be followed by another build failure. By this hypothesis, the numerous subsequent failures could be easily captured as soon as we observe the first failure. To evaluate this hypothesis, we did the second empirical study and found that 52% of failing builds are subsequent failures. Thus, a large portion of build failures are easy to predict once we observe the first failure. To achieve this goal, we propose our new approach called Smart Buildscape. Smart Buildscape follows a two-phase process. When a new build comes, Smart Buildscape first checks its last build status. If it is a failure, the build will be executed as normal. Otherwise, a predictor will be triggered and the build will be skipped if the prediction result is a pass. So take this timeline as an example. Since build 1 is a passing build, when build 2 comes, the predictor will be triggered, and for example, it predicts the build to pass. We will skip this build and save the cost.
We seem to be having a technical problem. We will try to check out what it is. Okay, so we seem to have an instance of Zoom crash on the presenter side. So we will try to switch to the recorded talk, and hopefully we will start somewhere in the roughly same position, and we will try to finish the presentation.
The Smart Buildscape first checks its last build status. If it is a failure, the build will execute as normal. Otherwise, a predictor will be triggered and the build will be skipped if the prediction result is a pass. Take this timeline as an example. Since build 1 is a passing build, when build 2 comes, the predictor will be triggered, and for example, it predicts the build to pass. We will skip this build and save the cost. We use the question mark to represent the predictor. Since the outcome for build 2 is not available because it is skipped, the new coming build 3 will trigger the predictor again, and this time, let's say the predictor correctly predicts it to fail and we run this build. Then the result shows it is indeed a failing build. In this example, our approach incorrectly predicts build 2 to pass, but we capture the failure one build later. Because build 3 is an executed failing build, our approach determines all subsequent builds as failing builds and execute them until it finds a passing build, which is build 5. This time, let's say the predictor predicts the remaining builds to pass and we skip the last 3 builds. The key for our approach is to differentiate first failures that happen right after a passing build. If we can detect first failures successfully, we can easily capture all subsequent failures. Based on our strategy and hypothesis, we explored features that focus on detecting first failures, such as the number of changed source lines, and use them for our random forest predictor. Then we evaluate our approach in an experiment of saving cost in real-world simulation. In this presentation, we report 3 highlighted techniques. HW17 is a state-of-the-art technique. Our approach of SBS is a customizable technique that can be tuned based on different sensitivity to bit failures. In this presentation, we propose our approach with 2 versions, under the safest configuration and the most balanced configuration. We measured 3 metrics in this evaluation. Take our timeline as an example. We measured saved builds as a proportion of builds that are skipped among all builds. For each observed failing build is a proportion of failing builds that are correctly predicted and executed among all failing builds. For each failing build that was incorrectly predicted and skipped, we also try to understand when it can be observed. So we also measured its failing build delay as the number of builds that were skipped until the predictor decided to build again. In this example, it is the interval between build 2 and build 3, which is 1 build. Here is the result. We can find that though HW17 saves almost all costs in CI, it only catches 2% of failing builds because it almost predicts every build to pass and skip it. This also results a high delay. In other words, it loses most of the value in CI. This is because the existing technique strongly relies on the information of last build status. When it observes a pass, it will very likely to predict the next build to pass based on the last build status. Then the next build is skipped and its build status is never known to the predictor. So the predictor is likely to continuously predict every coming build to pass, making it a vicious circle. Our approach resolves this limitation because our predictor doesn't rely on the information from the last build. Our approach under the most conservative configuration can capture 80% of failing builds, and it can also save 45% of computation cost. For those skipped failing builds, the observation will be only delayed for 1 build. Our most balanced approach can save 61% of builds and detect 73% of failing builds. The delay for skipped failures are 2 builds. We can also get a sense of the trade-off between cost saving and failing build recall. The higher benefit in cost saving will bring in higher risk to delay the observation of failing builds. To summarize, our work tries to reduce the cost in CI by skipping passing builds. The main contribution in this paper is differentiating between first failures and subsequent failures, study the prevalence of build and failures, design smart build skip that uses a 2-phase prediction strategy, evaluate our approach and compare it with existing techniques. Besides, there are also a lot of other experiments, such as feature selection and simple predictors, which are not included in this presentation. Please feel free to explore their detail in our paper. That's all. Thanks for listening.
Thank you. And thank you to the audience who sat through the technical issues. So I'm going to forward a few questions because we still have a little bit of time. How risky is it to miss a failing build? Will it add horribly to the process of debugging?
Yes, failing builds is always a very big risk for many companies. And according to the existing work, the delay of the observation of the failing builds could be even more than 4 times, cost 4 times more than build saving. Also, because our technique could detect most of the failing builds, and for those missing failing builds, the delay will only be 1 build or 2 builds, So we try to minimize the cost for missing a filling build as well. Thanks for the question.
Okay, thank you. So due to the time, we are going to skip the remaining questions, and then we will ask you to look for the presenters of this session in the lobby's video chats during the third hour so that you can continue the discussions and questions. You can also visit the demos, attend the student research competition presentations, the AMA sessions with John Grundy, and there is also a Google booth. So thank you and enjoy the rest of the conference. I will wrap up the session P14 here. Thank you again.
Thank you.
Okay, so thank you everyone for joining this session. This session is software development. I'm session chair Minghui Zhou from Peking University. We will have 5 papers in this session, 2 journal first, 2 technical papers, and 1 demo.
Hi everyone. So welcome to the P16 session. I'm Li Minzhang from UC Dallas. So I'm there will be 5 fantastic presentations on security and learning in this session. And please note that there's a delay in the actual streaming service compared to the actual Zoom session where the speakers are in. So you may want to ask the questions on further when we have them. Okay? So our first talk is about software validation and data transfer learning for effective software defect prediction. The presenter is Jun Chen. So Jun, you want to start now. The presenter is Jun Chen. So Jun, you want to start now.
Okay, so let's start our first talk. Goguryeo Zhao, won't you please take over? Okay, so let's start our first talk. Goguryeo Zhao, won't you please take over?
Hello everyone, welcome to my presentation. My name is Goguryeo Zhao. I'm going to present our work about improving the pull request review process using learn-to-rank algorithms. I'm very happy to work with Professor Daniel and Lenka da Costa and my supervisor Inzo at this work. So pull requests are used by developers to submit their contributions into central repositories on GitHub. Reviewers are responsible for reviewing pull requests and giving final decisions about whether to merge the pull request into the central repository or just reject the pull request. Code reviewers ensure the quality of the merged pull requests. However, we observe the workload of code reviewers keeps on increasing over time, as shown in this graph. The blue line represents the number of open pull requests that are waiting to be reviewed every day in our studied GitHub projects. While the orange line represents the number of reviews that a reviewer made every day. So it stays around number 5. So what we can tell here is reviewers, they have to pick 5 out of more than 20 open pull requests to review. So code reviewers, they need help to prioritize the open pull requests to select the one they have to review first. So an estimate of the time taken to review pull requests may guide code reviewers to prioritize pull requests. In our study, we observed there are pull requests that take a long time to review. As shown in this beam plot on the left, this beam plot shows the time taken to make decisions on pull requests. At the top of this graph, it has pull requests that take more than 400 days to be reviewed. While on the bottom of this beam plot, we see there are pull requests that can be reviewed within a day. So we think we can increase the reviewing throughput of reviewers by recommending them the pull requests that can be quickly reviewed. So we use learn-to-rank models to rank pull requests that can be reviewed quickly to reviewers. Then in the scenario where a reviewer think, okay, I only have 15 minutes now, which pull request should I quickly review now? So then the pull request ranked by our model can help them to pick a pull request to start first. So we select Java projects with more than 500 pull requests to evaluate the learn-to-rank models. We further exclude deleted and forked projects. We also excluded projects that do not use pull-based development. In the end, there are 74 Java projects are selected. Then we use the selected Java project to conduct our empirical study. We use historical pull requests to train and validate the learn-to-rank models. We use 4 dimensions of metrics to quantify a pull request. First, we use the textual information of a pull request, its title, and its description. We also use the source code that are changed in the pull request, and we also measure the experience and social connection of the developer who submitted a pull request. So in our first RQ, we observe the random forest model has the best performance in ranking quick merged pull requests. In the second RQ, we compared the random forest model with existing baselines, first in, first out, and small first. We observed that the random forest model outperforms the existing baselines for ranking quickly reviewed pull requests. In the third RQ, we found the social connection metrics of developers are the most significant metrics in affecting the performance of our learn-to-rank models. The most two important metrics are social distance and followers. Social distance isn't the physical social distance we're trying to keep now. It's the social network distance between developer and reviewer. And also the followers means the number of followers that a developer has on GitHub. The implementation here is reviewers should focus on the pull requests that are from their closer social circle when they're planning to take quick decisions. In the fourth RQ, we conducted a user study. We asked code reviewers on GitHub about their opinion about our approach. We observed majority of reviewers state that our approach could help them prioritize pull requests. For example, the first reason our approach can help reviewers to merge more pull requests in a limited time. Also, our approach can help reviewers to prioritize potentially quick reviews besides the size and age of pull requests. Also, our approach can prevent several pull requests from being blocked by a very single time-consuming pull request. So this is the end of my presentation. Thanks for your listening.
Okay, thank you, our speaker. It's an interesting talk. I do see one question for the speaker. Please listen carefully. How you select the GitHub projects to get to the final 74 projects?
Oh, so let me go back to my slide. So we started with Java projects that have more than 500 pull requests. We select Java projects because we have to analyze the source code in our approach, and we only focus on one language. So suppose we can work with other languages, we can include other language projects in here too. And we use 500 this number because this number has been used in existing work to exclude toy or personal projects, these non-popular GitHub projects. So then from this, as this start, we also further exclude deleted and forked projects from this selection. Then we further exclude projects that do not use pull-based development, that then manually merge every contribution, then don't merge contribution on the pull request level. So in this case, the pull requests are full of noisy, so we exclude these projects too. And in the end, 74 Java projects are left. Thanks for the question.
Okay, I do have one question for you. In practice, do the developers use the algorithm to rank the pull requests?
I think nowadays they do, because I mean, developers means they want to check other developers' work. And suppose they have a very limited time at a day. Like, okay, so it's like I have to finish. I want to finish a pull request today, and I don't want to have a very long pull request to work. So our approach can help them. Also, in other scenario, other approach can be helpful too, because I know there are approaches that can help developers select the pull requests that are most significant to the project. Like this pull request can bring the most value to your project, so select it. I think developers, they do use this criteria to select the pull request. So.
Okay.
Thanks.
Thanks a lot. Okay, let's switch to the next talk. Next, we will have Amisu Bosu from Wayne State University. The talk she's going to give is understanding the motivations, challenges, and the leads of blockchain software developers is the way. Okay, let's welcome Borsui.
Okay, so can you hear me now? Okay, so let me hide the video.
Yes, we can hear you very clearly. Please start.
Okay, so this is Amyangshu Boshu. I'm from the Wayne State University. And today I'll be talking about the motivation, challenges, and needs of blockchain software developer. So most of you probably have heard about Bitcoin. This is the leading cryptocurrency. And there is also other cryptocurrencies as well, like Ripple, Ethereum, Cardano, Litecoin. Those are. Now, the technology that enables this cryptocurrency is named blockchain. In simple terms, blockchains are chains of blocks. So each block contains a data, timestamp of creation, and hash of previous block. As a result, if you change one block, it will invalidate all the subsequent blocks. So in simple terms, we can say that blockchains are a kind of linked list where the link is based on the hash of previous block. Now, blockchains have several characteristics that make them very useful for several domains. First, blockchains are distributed and decentralized. Therefore, a single entity cannot control the data written in a blockchain. Second, blocks are immutable. So therefore, once written, it cannot be altered later. Third, blockchains ensures accountability using cryptographic keys. Finally, blockchain transactions are transparent to all the parties. Now, due to these characteristics, blockchains have potential applications in several domains. We already saw cryptocurrencies and financial domains, and other include like managing supply chain data, identity management, managing medical records, and land registry management. Now, due to the promises shown by the blockchain, the number of blockchain projects on GitHub has been increasing rapidly. So for example, in 2018, January 2018, when we conducted this study, a number of blockchain projects was 2,000 in GitHub. Now, 18 months later, when I was preparing this presentation, that number has increased more than 5 times. Now, actually, there is little known regarding the software development practices of blockchain project. There has been little bit study done on those things. Now, if these projects are indeed different from non-blockchain projects, then their tools and techniques developed for this non-blockchain project may not work well on these projects. So that's what we want to find out. Is blockchain software development different? We also wanted to find out the motivation, challenges, and needs of blockchain software developers to guide future research. Now, on this goal, we surveyed the contemporary blockchain developers since they have the first-hand experience of regarding the software development practices of blockchain projects. So we identified 145 projects from the GitHub. These projects have at least 10 stars and at least 5 distinct contributors. By mining the Git commit logs, we identified 1,604 developers that have committed at least 5 pull requests. We sent survey invitation to them, and we received 200 responses, so response rate is 13%. We excluded 44 incomplete response and had 156 responses for analysis. 37% of our respondents come from the top 10 blockchain projects like Bitcoin, Ethereum, SIA, and others. So more detailed list is in the paper. So now let's look into the results. So due to time limitation, I will present only the few key results and the highlights, and more detail. You feel free to read the paper for the more detailed analysis. So first question is blockchain software development different? So 93% of our respondents say that yes, developing a blockchain software is different from a non-blockchain project. And we also asked them how this is different. So they say that a higher emphasis on security and reliability marks the key differences. The second key difference is the uncommon characteristics of the blockchain software domain. Now, we also asked them, okay, what are the key challenges you face? So again, they say that the uncommon characteristics of the blockchain software domain, so 60% of the respondents say that uncommon characteristics of the blockchain domain poses key challenges to them. So what are those uncommon characteristics? So these uncommon characteristics is high cost of defects. So a defect in a blockchain software can cause like hundreds of millions of dollars. Then it's just technological complexity, distributed, decentralized, hostile developed environment, rapidly changing ecosystem, difficulty in maintenance, and steep learning curve. So we asked them, okay, what is the key needs of the blockchain developer? And they say that testing support is the key area that marks their primary need. So in conclusion, blockchain software development is somewhat different from non-blockchain software development due to several uncommon characteristics of the blockchain domain. Those differences are also primary source of challenges to the blockchain software developers. Developers need an array of tools to be developed where better testing support remains their primary need. So this paper has been published in the Empirical Software Engineering Journal, and many other key results and like actual response or excerpts from the developers are included in this paper. Thank you. And I'll be happy to answer any question.
Okay. Thank you, our speaker. So I do not see any questions from Slido, but I do have one question for our speaker. I think it's very interesting to look at the differences between blockchain applications and other applications, but the uncommon characters you list for blockchain applications, do you think they have similarities with the, for example, safety sensitive applications?
Yes. So we actually looked into those things. So now, like we asked these developers, and these blockchain developers, most of them are fairly like have more than 10 years of experience in traditional software development. Now, if a software developer, his traditional software development experience comes from like financial domain, banking, or maybe like say airlines, aviation. In these domains, or let's say medical software, where safety is very critical, then they will not find like there much a difference between blockchain and non-blockchain software. But most of the developers, most of the traditional software development ecosystem doesn't have that kind of like higher emphasis on security, reliability, and like zero tolerance of bug. So that's most of the traditional software development domain doesn't have. And that's why most of the people who come from traditional software development domain, they find that blockchain software development is different. Actually, in the paper, we also compared their practices and thing in details against like 3 different types of software development from the Microsoft. So there we also found out like what are the areas that marks the difference, what the blockchain developer says and what the Microsoft developer says. So please read the paper. There are more detailed analysis about like this kind of thing.
Yes, I understand. My point is these characteristics might not be new. They exist in the traditional industry, such as financial applications.
Yes, some of the characteristics remain, but some of the characteristics, like for example, decentralized hostile environment. So blockchain software is it's a run on a distributed machine. So it's called EVM or something like that. So this, for example, many of the banking software, they runs inside their local net. It's not open to the internet. But these blockchain softwares, they are open to the internet. So even the parties that are validating transaction, some of them can go wrong. So that means it's more difficult for them.
Okay. Okay. Thank you very much. Okay. So next, we will have SM6Soft distinguished paper. Our speaker is Saudi Chattopadhyay. Wow, that's very challenging for me to speak. He's come from Oregon State University. The title of the paper is A Tale from the Treacherous Cognitive Biases and Software Development. Okay, let's welcome our speaker.
Okay. Hi, I'm Solidity Chattopadhyay. I go by Rini and I'm from Oregon State University. And as Mingui said, we're going to talk about from the trenches how cognitive biases affect software development. So what are biases? Biases are systematic ways in which our brain deviates from processing information in optimal ways. An example can be confirmation bias, where we seek to look for and interpret information which confirms a hypothesis we already have. For example, you see the triangles believe that the squares are always blue, but they are selectively filtering out information that is not around in their surroundings. So these biases are embedded in our brain, and it is a way for humans to find solution quickly in a complex world, right? And developers are humans too. So developers also encounter these biases. For example, let's take Alan. So Alan gets a compiler error, and he hypothesizes that it's due to how the functions are defined. And so while changing the function definitions, he gets fixated and takes his time in refactoring the entire code. And he gets so fixated that he overlooks the issue that his environment is outdated, and a simple reload would have fixed the issue. So now he has to go back and reverse some of the changes that he already had made. So this led us to ask questions like, how do cognitive biases actually manifest in the real world? How does it affect developer decisions and actions? How frequently does it affect, and what types of biases do they encounter? And then if they do encounter, how do they overcome the biases to successfully complete the tasks? To answer these research questions, we conducted a field study where we let the developers go about their daily life without intervening much, and we were mostly a fly on the wall. There were 10 developers that we observed, pardon me, and we recorded their screen and decision process and thinking aloud. We then qualitatively encoded our observations to identify actions from left to right. That's navigation, reading, editing, executing, and ideating. And then we matched each of these actions to certain biases. Either they're present or no biases when there were nothing present. And then we went out and did some interviews with 16 developers from 3 different companies. And we asked them, how frequently do you think developers act under biases? And what do you do to fix them? I would like to mention here that there is a huge role that gender plays in how it affects biases. However, we were only able to observe 2 women and interview 3 women developers, which prevented us from making any conclusions regarding gender and bias. Moving on, so to do the analysis, we categorize the biases based on the type of effect it has on developer actions, based on their definitions, and based on existing literature. For example, the preconception bias category talks about biases that makes developers select actions that match with their preconceived mental model, like the squares blue and the triangles that we talked about. Another category is fixation, which talks about biases where developers fixate on initial assumptions or hypotheses and overlook other cues that are in their environment. And the third one is convenience bias, where developers made false assumptions and premature conclusions, often opting for a quick fix rather than a more costly process. There are 10 such bias categories that we identified. but we'll only talk about the first three. So the first question we asked is, how does bias affect developer actions? We observed a little over 2,000 actions, and out of those, 953 were associated with biases. That's around 42% of the actions. However, biases doesn't necessarily mean that it's bad. So to identify the negative effect of biases, we introduced the notion of reversal actions, any actions that needed to be undone or reversed at a later stage. When we compare reversal actions and biases, we see 759 of the actions that are associated with biases needed to be reversed, whereas 786 of the actions that were not associated with biases never needed to be reversed. So we find that about 45% of the actions are biased, and not only are they biased, these biased actions are also more likely to be reversed at a later stage. So then we asked, which of these biases occur frequently? Here you see a map of the bias categories and the number of actions that were reversed that are associated with it. And the one that stands out the most is fixation. Fixation resulted in almost 90% of the actions reversed. These are cases where developers fixated on specific solutions, hypotheses, and rejected warnings that are in the environment that contradicted their belief. For example, let's take Paul. Paul got a connection error and hypothesized that it's due to the architecture of the system, and he spent a significant amount of time trying to reconstruct the architecture so he doesn't get issues in the future. However, he overlooked the issue that it was because he was fixated, he didn't consider that it was from the API side that he was trying to connect to and not his own infrastructure. So then we went out and asked the developers, how frequently do you think developers act under each of these biases? The left side, where CB10, CB6, these are the bias categories, and memory bias, which is CB10, was associated with most developers believed that 75% of the times developers often or always act under memory bias. The second, third, and fourth biases are the preconception, fixation, and convenience bias that we talked about earlier. So then we asked the developers, how do you overcome these biases or the negative effect of the biases, right? And there are certain interesting answers that came up. One of them was, for example, in preconception, developers believe that days which are not focused on code, for example, documentation days or test fests, these days can help us break out of our preconception or hypothesis and focus on other things. Another example can be maintaining proper journals and diaries, and those also help us self-reflect on the preconceptions that we have. Another bias is like convenience bias that we talked about. Practices like early consistent feedback, like design review, code review, customer review, or sprint meetings also help us catch these convenient quick fix decisions that developers make early on, as well as having standard practices like impact analysis implemented across the organization also help prevent convenience bias. Another reason for such high percentage of developers agreeing with the bias is they pointed out there is a lack of tools that target each of these biases in their work. For example, for fixation, a developer pointed out that if an IDE can detect that you always get the same error and you're always working on the same part of the code, say 5 times, 6 times, and then if the IDE can detect that, they can say, hey, you're getting the same error, maybe you can try something different. Another tool for optimism bias. Optimism bias is where developers were optimistic about the change they made, and they wouldn't consider all the effect of the code changes that they make or other consequences. So a tool that can continuously run tests in the background can say, hey, this is the area of the code that you haven't run any tests on, maybe consider running a test here. So to conclude, we find that almost 45% of the actions developers take are biased, which lead to a lot of rework, loss in time, a lack of exploration, even having a hard time maintaining context as they have to constantly go back and preserve and recall the context that they were working with. More or less, developers are aware that biases exist and they exist at a very high rate. However, they do say that there's a lack of tools that can help them. So we compiled a set of practices and a wish list of tools that can help developers mitigate the effect of the biases. Lastly, I want to thank my wonderful co-authors and participants from Face Change and additional interview participants from IBM and Etley for helping us conduct the study. Thank you for joining from different time zones, and I am happy to take questions.
I guess I will take over. It looks like our session chair, maybe her Zoom crashed or something. So I'll ask you a couple of questions. First question is, there are multiple studies in psychology and computer science indicating that self-reporting may not be reliable. How did you mitigate this effect in your study?
So our first study was the observation study that we conducted when we went to a company and we observed developers go about their daily task. We didn't give them any tasks. It was we just observed them go about doing what they do daily. And then we identified biases that were present after qualitatively coding that data. So that part wasn't self-reporting. The part where we went out and asked interviewers about whether or not they think biases exist. We tried to mitigate the self-reporting by framing scenarios of developers who are in certain positions and describing a bias in a scenario, asking how would you help this person, what practice would help them, or what tool would help them. And so it was a slightly different perspective, but of course, in like any other study, interviews and surveys, self-reporting limitations does apply in this study as well.
Great, thank you. I'll ask one more question. How can we distinguish between a bias versus a mistake?
That's a very good question. So biases are, there are certain biases we could identify it. If there were actions that were deliberately taken. For example, in fixation, if the developer was saying out loud, I know the bug is here and I've dealt with this before. Or if they're deliberately ignoring certain warnings because they're just used to it, then we classified it as a bias. For other biases like memory or ownership, it's harder to differentiate between what a bias is and what a mistake is. We did not identify any mistakes per se, but there were 3 cases in the entire data set where the developer out loud said, oh, I made a mistake. So we eliminated those from the data set.
Okay, thank you. I'm sure that there's going to be more questions regarding those, and I can see there are other questions that I just can't get to. So I encourage everyone to join the speaker after the session or in the 3rd hour. And these questions will be archived in their chat, and they can start a video chat there, and you can speak with the authors there. But very interesting work. Thank you very much.
Thank you.
So our next speaker is Sanjay Huang, in his work on gap between theory and practice, an empirical study of security patches in Solidity. Go ahead and take over.
Okay, thank you. Can you hear my voice and screen?
Yes, I can.
Okay, thank you. Hello, everyone. This is Songjay Huang from KAIST. I'm pleased to present our work on an empirical study of security patches in Solidity. This is a joint work with my advisor, Seok-Young Yu. So what is the Solidity? Solidity is a high-level programming language used to implement smart contracts. And the smart contracts are programs running on a blockchain platforms. So since smart contracts are programs, they may contain bugs and security vulnerabilities. As shown in this slide, many security issues have occurred in real world, and these security issues led to financial loss. So the security of smart contract is very crucial. And due to the tremendous interest in smart contract security in both academia and industry, the vulnerability in smart contracts are well analyzed and disclosed publicly. Then how many known vulnerabilities are patched by the Solidity compiler? To answer the question, we first collected known vulnerabilities from 5 different sources, including the official Solidity documentations, projects from blockchain companies, and 186 academic papers that contain smart contracts in their titles and abstracts. So altogether, we collected 41 known vulnerabilities from these 5 sources. And by checking release notes of the Solidity compiler and by dynamically testing our test code, we revealed that 7 of them are patched by the Solidity team and 1 patch is under development. The patched vulnerabilities are shown in this table, and all the security patches are adapted from the Solidity version 0.5.0. So 0.5.0 should be used in order to avoid known vulnerabilities properly. So given that the Solidity compiler has security patches, do the patches really enhance the security of smart contracts in real world? The answer is no, because developers do not use the latest compiler. We check whether contract developer uses the Solidity version at least 0.5.0. To investigate it, we first collected 55,046 real-world smart contracts from Etherscan and analyzed them. The analysis result is shown in this table. It is surprising that only 1.86% of smart contracts use the smart Solidity version 0.5.0 or larger. This means that 90.14% of smart contracts are not protected by the security patches in the latest Solidity compiler. And this could be a serious problem because the Solidity version below 0.5.0 cannot prevent known vulnerabilities automatically. So if developers do not handle them manually, various security issues can arise. So to understand how many live contracts are exposed to the known security vulnerabilities because of missing security patches, we developed a static analyzer that detects vulnerable contracts. By running our tools on 55,046 live smart contracts, we found that 4,632 vulnerable contracts that have received and sent more than 10 transactions. The last column shows that the total number of transactions of these vulnerable contracts are very high. So this indicates that these contracts have been actively used. And we manually investigate these vulnerable contracts to understand the developer's common mistakes and whether the Solidity patches are sufficient to prevent known vulnerabilities. Our manual investigation revealed many patterns of developer mistakes. And due to the time limitation, I will explain only 2 vulnerabilities, the first one and the third one. Please refer to our paper for more detail. The first vulnerability is misusing constructor by incorrectly naming constructor functions. So in Solidity, a constructor is a special function that is used only once when a contract gets deployed to the Ethereum network and gets removed from the contract. The name of a constructor function must be same as its contract name. The Solidity patch for misuse of constructor is simple. A keyword called constructor is newly introduced, and now developer must use this keyword when they define constructor functions. And our manual investigation shows that developers often make typos in constructor names. So here the contract name uses the capital letter O, whereas the constructor name uses the lowercase letter o, which is a typo. And because the constructor name is different from its contract name, the function becomes a generic public function, and therefore external attacker can call this function to become the owner of the contract. So we call this developer mistake pattern as typo in constructor names. Another mistake pattern we found is incorrect reuse of standard contracts. So the Solidity team and well-known blockchain companies provide verified smart standards contracts so that contract developer can reuse them to build secure contracts. However, we found that developers make mistakes in reusing standard contracts. So in this example, the developers copied the token ERC20 standard contract, but changed it only contract name, not the constructor name. Similar to the previous example, because the contract name and its constructor names are different, the token ERC20 constructor becomes a general public functions, and therefore attacker can call this function to gain Postcoin for free. The current Solidity patch introducing the constructor keyword cannot prevent these 2 patterns of developer mistakes, so a better patch should be released additionally. There are 4 developer mistake patterns for misuse of constructors. For 109 contracts vulnerable to misuse of constructor, we manually confirm that 55 contracts are exploitable, and the total number of transactions for this exploitable contract is 64,674, and 13 of them have more than 100 users. And we report this vulnerable contract and assign 4 new CVs. The next vulnerability is storage variable shadowing confusion. Currently, there is no patch for these vulnerabilities. So here we have 2 contracts, the standard token and USDX coin contract. The USDX coin contract is a child contract of standard contract. Standard token contract. They both have a variable named total supply. So the variable in a child contract shadows the inherited variable. The problem is that the function bound in the parent's contract refers to the variable total supply defined in the parents, whereas the function min token in the child contract refers to the variable total supply defined in the child. So the function bound reduces the total supply defined in the parents, while the function min token increases the total supply defined in the child. We call this pattern the function complete pattern. So we found 6 kinds of developer mistake patterns. And these mistakes can lead to many problems such as confusing owner addresses and referencing the contracts. And among 231 vulnerable contracts, we manually confirmed that 106 contracts are exploitable, and the total number of transactions for this exploitable contract is 292,048. And among them, 26 contracts have more than 100 users. And we report contract vulnerable to variable shadowing confusion and receive 2 new CVs. So because developers make lots of mistakes due to the variable shadowing confusion vulnerability, we believe that a patch for this vulnerability is necessary. So in summary, we observed that many developers do not adapt the Solidity patches properly. Our study shows that it is important to use the latest version of the Solidity compiler. And we need more effective security patches than the current Solidity patches because some of them cannot prevent their targeted vulnerabilities. And also more security patches are necessary. So thanks for listening, and I'm more than happy to take questions.
Okay, thank you for the very interesting talk. I'm sorry I missed the earlier one. I think it's a very unique experience for everyone. And thank you everybody for your great work. Okay, I do not see any question from Slider, but I do have a question for you. The question is very basic. You talked about developers do not get Solidity patches. My question is why? It looks like your empirical study shows that those patches are very critical. If so, why the developers do not take those patches? There must be a reason. For example, they may not be that critical, or what?
Yes, that's very great questions, but unfortunately, that was not our research scope, so we did not investigate why developers did not patch a solid security patch properly. So we postponed.
Do you have a very basic hypothesis for that?
Pardon?
Do you have a basic understanding or hypothesis for that? Why they do not do that?
Okay. So we did not explore this, so I'm not 100% sure.
Okay.
But I'm guessing that the Solidity developers are not expert in the security area, so they don't know about the security vulnerabilities. So they may not even know there exists some security patches from Solidity. So that is the reason why, one reason they do not use the latest Solidity compiler, and they may not understand the importance of using the latest versions of compiler, because if they upgrade the compiler version, they have to test their code again. So they may not like this at first. So they keep on using the older versions of compilers for the reliabilities of their program.
Okay.
It's my opinion, but I'm not 100% sure because that was not our research scope.
Okay, I think it's very interesting to explore because that's a very basic question for this study to go further. Okay, thank you very much. Now we have the last talk. It's a recorded demo. Two demo. Thank you. Please play the recorder. And this demo is from David Roy University, Washington State University. The tool is vitals, visualizing, eye tracking, and biometric data. Thank you.
Welcome to our paper presentation for the ICSI 2020 demonstrations track. We present Vitals, a visualization tool for biometric data in software engineering. Software engineering research has entered the neuro age. Recent research in empirical software engineering is applying techniques from neurocognitive science, and it's breaking new grounds in the ways that researchers can model and analyze the cognitive processes of developers as they interact with software artifacts. Researchers in the domain borrow techniques and tools from neurocognitive science, like brain imaging and eye tracking technology, to model these cognitive processes. However, given the novelty of this intersectional research, there are no tools to support the multimodal nature of the data being collected. Researchers need tools to help them analyze and visualize biometric data, like gaze fixations and cognitive load, as they change over time, and as a developer reads source code or interacts with different software artifacts. Vitals was born out of this need and has several highly customizable and interactive features. For example, it is the first tool to support synchronized biometric data for source code elements, and it displays this data as a heat map over the source code. The heat map supports temporal brushing for time-specific analysis. Vitals also allows researchers to annotate points of interest in their experiment data, and it displays custom metrics to support their analysis. Here is the main screen of Vitals. I already loaded a sample dataset which contains the eye tracking and brain imaging data of a participant reading a C# file. In this example, we are using data from an FNIR device. The main area displays the source code artifact used in the experiment, along with a gaze heat map overlay. A graph of the FNIR data can be found at the bottom. The heat map can be customized. This mapping, as well as the mapping of the data to the line graph, is completely customizable. Once configured, you can temporally explore the data. The heat map and the line graph are synchronized along the time axis. We can brush a portion of the line graph, and the heat map is updated to reflect the data captured in the time frame selected. Vitals also allows researchers to select and annotate portions of the source code. These annotations can be used to highlight areas of interest and then saved and used for further analysis. The annotation feature combined with the visualization make Vitals very useful for conducting post-experiment interviews. Researchers can visually analyze the data to gain insights that inform the questions asked in the post-experiment interviews. And the source code can be annotated directly to incorporate participant responses as well as researchers' notes. Research in empirical software.
We are sorry about that abrupt video. We had to keep it short. But I'm here for any questions that you guys have about Vitals.
I do not see question from Slider, but I was interested whether or not you open source your data somewhere so everybody can use it.
Oh, are you asking if we open source our data?
This kind of data is a lot easy to collect, right? If you can open the data for everybody else to use, well, it's wonderful.
True.
Are you planning to do that, or you already have done that?
So we have released a sample data set so that people can download Vitals and play around with it with the sample data set. And then then they can decide if they want to use their own data with vitals. So we just have one sample data set.
Okay. There are some questions from the slider. Okay, very cool. Does it include the file explorer and other IDE features?
So it doesn't, but you can view multiple files. So it wasn't shown in the video, but you can have multiple tabs of source files and like switch between them and such. We might add a file explorer in the future, but currently it does not have a file explorer.
No sound. Okay, there is one more question. I'm not sure if you can hear me clearly.
I can hear you. Can you hear me?
How is the visual information captured? I assume special equipment is required. I think so.
Yes, for sure. So Vitals is specifically targeted towards people that have eye tracking equipment. And actually, that's all you need to use Vitals. But if you have some other biometric equipment, such as like fMRI, FNIR, or even a heart rate monitor or a wristband electrodermal sensor, you can synchronize that data with the eye tracking data. And that's when Vitals really shines. You can visualize both the eye tracking and the biometric data right on top of the source code.
Okay, wonderful. By the way, I'm interested, have you done any research on this kind of data?
Yes, so our lab at Washington State University primarily works with an FNIR device and an eye tracker. In the past, we've studied bad practices in software development, specifically linguistic anti-patterns, and seen if that results in a higher cognitive load in the developers. And we were able to show that it does. Like if you have bad lexicon in your source code, people are going to struggle more to comprehend it.
Okay, sounds great. Okay, so that is the end of our session. So thanks everybody. Thank our audience for your patience, and thank our working team for the great job conducting this virtual conference. This is really, very unique experiences. Sorry, I made so many mistakes. So enjoy the rest of the day. Thank you. That would be all. Thank you. If there is any further questions, you can always find the presenter in all kinds of sessions as soon as you go fast. Okay, thank you.